Welcome into the Tech Ed Podcast. I am your host, Matt Kirchner. We have a wonderful episode in store for you this week, talking all about emerging technologies in advanced manufacturing as we reach the world of technical education, as we reach the world of manufacturers who are doing innovative things in their space and putting those people together. I can think of no better individual to share some of the great things that are happening with regard to research, with regard to emerging technologies than Dr. Bill Peter. Dr. Peter is the Director for Advanced Manufacturing at the Oak Ridge National Laboratory. And Bill, it is awesome to have you with us. Thanks for joining me.
Thank you. Thank you for having us and getting a chance to talk about some of the things we're currently doing and how it's having impact with workforce development.
Absolutely. And having that impact on workforce development, we all know is so incredibly important, especially in this day and age when manufacturers are looking for incredible talent and not always finding it every place that they're looking. And so we've got these huge opportunities for young people and people of all ages to find great careers in advanced manufacturing. And I know you're doing just a tremendous amount of work in that space. Before we get into that work, I want to ask you this, and I know you've got an interesting background. You grew up all over the Eastern United States. Tell us a little bit about how did you learn the craft of engineering?
So growing up, I actually had a huge interest in building and construction. My grandfather was in manufacturing, had run facilities in Mexico, in the Ohio area. That was one thing that had really perked my interest in the area. My dad had always been in business, and so I always had this sort of split scenario of would I go into business or would I go into engineering? Mm-hmm. I think I love problem solving, though, and I think that's really what drew me to the area. And one of the things to me that in manufacturing, why it's drawn me down that direction is the fact everything we touch every day is made, and trying to understand how those things come to be. And so that really led me down this pathway.
You know, I think a lot of times folks that maybe didn't spend their time growing up in and around manufacturing as you did don't always have an appreciation for all the problem solving that takes place in manufacturing, all the fascinating different career opportunities that they are, and also the opportunities to port from maybe other disciplines into manufacturing. So here you're somebody who is studying civil engineering, and when I think of civil engineering, you think of urban infrastructure, you think of bridges, you think of roads, those kind of things. And through that fascination with materials and failure of materials and so on, finding your way into manufacturing, where interestingly enough, your grandfather spent his career. It is fascinating to me how people can find these different routes into the world of manufacturing. So that leads to this opportunity with the University of Tennessee, with the Oak Ridge National Laboratory, which I understand is abbreviated ORNL. Is that right?
That is correct. Being a federal laboratory, we love our acronyms.
Yep, right. Absolutely. Well, in education, we do as well. So, just whether it's a show that we're at, whether it's a trade organization, whether it's a program, whatever, they all have letters. And in your case, ORNL. So we'll use that as the acronym for the Oak Ridge National Laboratory. Tell us about this and specifically the manufacturing program and what you're trying to accomplish.
Yeah, so the Oak Ridge National Laboratory, we have a significant amount of advanced manufacturing research activities, everything from looking at battery fabrication to how we could think about substitute materials for critical materials, to looking at how we recycle and look at sustainability. Some of the areas, though, that we're spending a lot of time in more recently are in areas like composites and carbon fiber production, additive manufacturing, machining. And in fact, our program today is really focused around smart manufacturing, automation controls, using additive manufacturing as a tool in the toolbox, and how do we merge or converge multiple manufacturing technologies together to help with agility.
I love that way of looking at it. And, if you look 10, 15, maybe 12 years ago, and everybody was getting excited about 3D printing, additive manufacturing, and a lot of manufacturers were having a hard time finding where the overlap was, or is this really going to replace things like machining or metal stamping or what have you? And our message was always, look, we're not going to replace those technologies, but there are ways to augment it through things like work holding, finding new applications for materials, maybe things that we can't do in certain metals that we're able to do, for instance, in carbon fiber 3D printing. And I think we're at a point now where additive has found its place in manufacturing. And that's a really, really exciting time to be in the world of manufacturing as we see these emerging technologies. You also mentioned all the different applications that you're involved in. So I think about everything from whether it's composite materials and carbon, whether it's additive manufacturing. You mentioned battery technology as well. Hit on that just briefly, especially in this age where we're trying to figure out EV in the automotive space, where we're trying to figure out energy storage in a lot of different spaces, alternative energy, for example. What are you doing on the battery side?
So in the battery, Oak Ridge for quite some time has worked on things like lithium ion. I think there's two different approaches, one on how we look at transportation and coming up with batteries that have a smaller volume as well as way less and are more affordable.
Sure.
And then on the stationary side and thinking about large batteries. And so we're doing a lot of work in areas like sodium ion batteries, solid state batteries. That is where we're starting to think as we go forward and start looking at both the structure as well as energy storage. Can you start to combine those into the same materials as you start to fabricate them, as well as areas like flow batteries, which make a lot of sense as we start thinking about building construction and trying to look at stationary type energy storage.
So a really exciting time. I didn't realize you were that deep into the battery stuff. And when you mentioned that, I was like, oh, that's just another application for some of these emerging technologies on the material side that didn't occur to me. So thanks for filling us in on the. I also want you to fill us in on the manufacturing demonstration facility called the MDF, of course, another acronym for the ORNL.
Yes.
But I know you're doing a ton of cutting edge research in this space, and I know our audience would love hearing about maybe a recent breakthrough that you've seen as a result of the work that you're doing with the MDF.
So I'll start a little bit with the mission. We're trying to go through and look to see how do we help with the domestic supply chain explicitly as we look at clean energy. A lot of our components as we think about energy systems, transportation, buildings, even as we look at batteries and the grid, a lot of those are fabricated overseas, and we're trying to see where and how can we bring those back, making them affordable. We're also trying to think about higher performance and also integrating smart manufacturing, not just to large companies, but how do you get that integrated into small and medium enterprises and really be able to help be competitive in that space. And I start with that because I think it'll make sense as we start looking at some of the breakthroughs as we've been working inside that area. One of the areas that we've spent a lot of time lately is looking at large-scale metal printing. We already have been working heavily looking at large-scale polymer printing. In fact, at the entrance of IMTS is this strategy, which was something we did back in 2014, about a decade ago. Create a whole industry just on thermoplastic printing that usually has a fiber included in it to make large polymer parts. Got up to about 500 pounds per hour deposition rates in that.
Wow.
We're now getting into a lot more work in metal printing and have worked with companies like Lincoln Electric and others to look at deposition, GKN for titanium, looking at laser wire, Lincoln Electric for looking at arc wire type materials. In fact, we've now started taking that and going into that whole idea of different tools in the toolbox. One of the things we're showing here is the Future Foundries is a convergent manufacturing platform where we have machining, then we're integrating it with directed energy deposition or metal printing, with metrology, and with localized heating on a pallet system.
Okay.
The whole basis here is federation of the systems, getting it so each of those systems are talking to one another, and how do we automate and help with agility? So if I look at low production parts, how do we make it where it's feasible to go into low production parts and be able to automate those systems to work together?
Yeah, those are all things that are fascinating to me. And of course, our listeners are accustomed to hearing us talking about kind of those low volume, high mix manufacturing applications, which are much harder to automate than a situation where you're making the same part over and over and over again. So I can totally see where you've got the combination of additive metal, 3D printing, you've got machining, you've got a palletizing operation and so on. What's the application for something like that? So give us, you're working with GKN and Lincoln Electric. Those are some pretty well-recognized organizations in manufacturing. What's the end-use product, or what are you hoping that would come from something like that?
So there's a whole range, and it goes everything from, like with GKN, we've been working on titanium for aircraft components.
Okay.
Most people don't recognize as you get on a plane, there's been an increasing amount of titanium that complements the carbon fiber as we look on planes.
Lightweight and high strength, is that kind of the two combination?
As well as there's a concern on galvanic corrosion from the composites.
I'm an old plating guy, so you're starting to talk my language. Absolutely. Go ahead.
And so as we've done that, though, titanium is usually at very low yields. It's between 10 to 15% yields. But you do heavy machining, and part of it's because the complexity of the parts that you're fabricating. We take milled product or forged sheet, plate, what have you, and then go through and machine out the finished part. With additive, we can get much higher in yield. So you can get up to 70, 80, 90% yield. So the companies are spending a lot less time on machining and having a whole bunch of chips that you...
Are you talking about production yield?
Actually, material yield.
Got it. I wanted to clarify just to make sure. Yeah.
Appreciate that clarification. Yeah, it's material yield. So they typically call it buy to fly ratio, which you usually end up with a 12 to 1 buy to fly. 12 pounds are purchased, 1 flies away, which is very pictorial as you think about this. We're really trying to go through and see how we drive that efficiency, lower the overall cost for those aircraft components at the same time of going through and thinking about energy use and efficiency as we do that.
Sure.
Another application, though, in the steel is we have all types of metal componentry. And one of the big issues we see today is as I start looking at whether it's wind energy, whether we're looking at nuclear energy and trying to think about reactors. A lot of these large metal components we're pulling or having to bring overseas, and there's lead time issues. There's a lot of challenges as we try to think about how to innovate and make them better. And so we're spending a lot of time in looking at how do we fabricate these large metal components, typically steels, that we can go through and put into application at a lower cost. And to that discussion we had earlier, it may be that I take a cast product and add on to that cast product as we need to.
Fascinating.
One of the most interesting projects we have that's coming up is one that in which we're working with a pretty large team, Voith, Huntington Ingalls, arc welding, and going through and actually building Francis runners.
What's a Francis runner?
It's a complex turbine that goes into a hydro dam.
Okay.
And our access to those are limited in the U.S. It's hard to produce these in the U.S. And so we're trying to augment to see where and how. We're totally building this one additively. It's going to be between a 35,000 to 70,000 pound part.
Wow.
But the idea is to learn from this and understand where should we be using additive with other technologies to be able to build those complex shapes.
So it almost feels like in some cases you're trying to, you mentioned now, I think at least 3 times, manufacturing and production and engineering that's taking place offshore, right? And we're bringing that back and trying to bring that back to the United States, but not necessarily bringing it back in the way that it's being done, but leapfrogging the technology and finding new ways to find applications or to produce new applications for things we've traditionally done offshore, doing them here in the U.S., but doing them using advancing technologies. Is that a fair assessment?
That's a very fair assessment. Behind all this is the digital backbone to me.
Right.
And it is trying to understand where the proper technology comes in and how do I go through and use the information flow to better assess the situation. So a lot of the things that you'll see under our development are looking at smart manufacturing, how we extract data as we're actually producing these parts,
right?
Using machine learning to very quickly be able to go through and see when are we either out of geometry, when are we going to have various different defects in the component, and be able to figure out, can we actually get around that and do real-time modifications to the systems we're building.
Yeah, so it's the extension of the whole Industry 4.0 concept, which we've been talking now for 7, 8, 9 years, maybe even longer, about smart sensors, smart devices out on the edge. They can think for themselves. They can communicate with other smart devices. They're gathering tremendous amounts of data, more data in manufacturing than we've ever had before. A lot of folks that have kind of taken that first step into smart technology are like, okay, well, that's awesome. I'm collecting all this data. What am I doing with the data? And what you're telling me is that you're able to use those sensors and devices, the data that they're collecting, you're able to acquire that data, create a data set of some sort, and then utilize artificial intelligence and its subset machine learning to find patterns in that data, to predict future failure, to find anomalies in the process. Is that right?
That is correct. In fact, I'll give the example. In powder bed, we have a software called Peregrine.
So powder bed would be powder bed metal 3D printing, is that right?
Yeah, where we're either doing binder jet, laser, E-beam. You're taking a layer of powder, and you've either got an energy source or essentially a resin that you're going through and building up your component layer by layer. One of the things that we've done is we'll use high-speed near IR cameras as you're building up those parts, and we can image the defects real time as you're building those up. And as we do that, we can start to see little nuances, like maybe I have a parameter difference here, or the slicing software to dictate where that beam goes is changed, and be able to pick up those defects that are coming up from those different anomalies.
Very cool.
So it's almost like a born qualified type component. I can give you the digital file, giving you all the information of what's happened to that part when I finish building the part.
Well, let me ask you this out of curiosity, because a lot of times as we're working and talking to manufacturers, they're understanding. I mean, in your case, you're using, I'm sure, a lot of different sensors, devices, cameras, gathering this information. Well, what's the machine learning platform that you're using? I mean, as people think about, formatting it in Data Factory and using something like Microsoft Azure to analyze that data kind of at the cloud level, what are you doing with the data?
A lot of what we're doing is actually homegrown and developed, and then we're engaging industry as we develop it.
Okay.
And part of the reason I bring that up is it's tying in all the different pieces. So we've built our own slicer technology. We have over 200 users now using the slicer.
And slicer technology, for our audience, just give them a quick definition.
The slicer is basically the software that basically decides where and how the robot or the beam or the gantry is going to go to lay out or print that component in additive manufacturing.
Got it.
And so as you're developing that, and I want to get key features or feedback, you want to integrate these. And in fact, I think one of the strengths of the laboratory, we have the fastest supercomputer, so we spend a lot of time with data. We can handle large amounts of data.
Fastest in the world?
Fastest in the world.
No way. Wow.
Yeah, and we have advanced characterization and a lot of materials background. So we're taking those strengths together to basically build tools that we can go through and process this data and see what's going on. So a lot of it is built in our core at our place, and then connecting with industry on how does this work and how would you start to implement it.
Okay.
As we go through that, though, we understand not everybody has a supercomputer in their backyard. So trying to understand how we go to low order models and efficiency as we do this. And that's where a lot of the AI or machine learning activities come
Sure.
from it. We do partner with other companies. In fact, we have over 280 partnerships with industry.
Wow.
And so while a lot of the way we're handling the data may be at our own core activities, we are then looking to see can we work with other companies and try their software and how it would connect with what we're building.
Awesome. And then the goal ultimately is do you commercialize the research directly, or are you partnering with other companies that are utilizing your learning, or what happens next?
All above. So we're funded by the Advanced Materials and Manufacturing Technology Office out of Department of Energy. They support our core research. They also each year put about $2 million down for when a company comes in, looks at what we're doing, they can basically go through and write up collaborative research activity with us. This has made it really, really easy for companies to come in and try out the technologies that we're developing. I'd say we have unique relationships with the equipment manufacturers. We enter under much larger collaborative activities with those equipment manufacturers where they actually come into our facility, work hand in hand with us. And part of that is to try to make sure that when we finish the activity, it is seamless in the transfer of the technology. But the nice part is you're building off of that. I sort of see the equipment manufacturers as the upstream. That means that material providers, software providers, and end users can then all go and start using that equipment technology and try before they buy.
Yeah, I love that. And one of the reasons I'm enjoying so much our conversation here with Dr. Bill Peter, who is the Director of Advanced Manufacturing, for Advanced Manufacturing at the Oak Ridge National Laboratory, is, all the convergence of different technologies you brought up already. We've talked about additive. We've talked about subtractive manufacturing, meaning machining. We've talked about robotics and automation. You're talking about slicing. You're talking about software. We're talking about AI. We're talking about machine learning. And all of these things that, quite honestly, Bill, I've been saying for a long time, we're going to converge in the world of manufacturing, necessitating a whole new type of worker in manufacturing. All the things that we've been predicting and talking about are the exact things that you are doing at ORNL. And so I want to ask you this. I mean, as you look to, the next 2 to 5 years for the American worker, and as you look to bringing manufacturing and all these different applications from offshore into the United States, which are, it's great for employment, it's great for our economy, it's great for our national security. It's really, really important work. But it's not a one-sided equation, right? We've got an obligation here in this country to figure out what the next generation of worker is going to do. So not just an additive, although I want you to touch on that. But as you look at these convergences of technology and young people or really anybody who's interested in getting into advanced manufacturing, how is what manufacturers, or for that matter, those doing research in the manufacturing space, how is what they are looking for in their next generation of team members going to look different here in the next several years?
So I think the areas that I've already started to see a change in is areas like computation, mathematics, looking to better understand trends that you see within data. I think that's a key aspect that we're seeing that, when I was just getting started was not something, it was something you could do and there was modeling, but it was not a large area of interest. To me, something that has grown substantially and I think creates a whole bunch of new interest. With that, I still think you're going to have problem solving is still going to be very key.
For sure.
I think as we look at it, the engineering background, mechanical engineers, understanding how things work, that's an important aspect. Understanding your materials is still a very important discipline. But I think it's really that idea of understanding statistics, understanding computational tools is something that'll continue to increase and drive new opportunity for students.
So let me ask you this. I mean, does that mean that students need to be, in order to be successful in manufacturing, need to be full on like master's degrees in data science, or are there kind of some on-ramps and off-ramps we can think about for people coming into manufacturing at different starting points in terms of what they need to know?
Yeah, I don't think all of them need to have PhDs or masters in that space. I think it needs to be a various set of skills. I do think understanding interfaces with that information is something that'll drive, even for those on the floor, you'll start to see the scenario of being able to visualize data and understand it real time and how that modifies the overall system. I think those will be critical as we're starting to engage more and more of this practice. I think there's plenty of applications, though, for individuals that have great computer skills to get in areas like modeling and other activities, seeing the information and data, and may not even need advanced degrees as they get into a lot of those activities as well.
Couldn't agree with you more. And by coincidence, I was just having a conversation this morning with a gentleman by the name of Leo Reddy, who's the founder of the Manufacturing Skills Standards Council. And Leo and I were talking about the kind of skills that'll be important for the frontline worker. I mean, literally for the person coming into manufacturing. And I think you hit on some of them that are really, really important. That if I'm working at a machine tool, if I'm working on a production line that's combining additive and subtractive and other technologies, being able to understand data visualization. And by that, we mean it's not necessarily diving into a huge, large language model and going through every single line item of data. It's saying, all right, how can I read, things like graphs and other outputs from a human machine interface at the production line that's telling me information, data driven about how my line is performing, whether it's yield, productivity, cycle time, some predictive data or model that we have, and being able to at least interact with that data on a real down-to-earth basis, I think is going to be something that's really, really important. I know something that's really important to you is this new partnership that you have with the University of Maine. And I'd love to learn a little bit about this partnership that you have, and I understand it's unique, so maybe share with our audience a little bit how it might differ from some of the other academic partnerships you've been a part of.
Yeah, so one of the things we've been trying to look at is sustainability and trying to think about localized materials.
What is a localized material? Is that a material that's drawn from a local area?
Local area. Yeah. So instead of thinking about centralized manufacturing, are there opportunities where you could look at what local resources I have and be able to use those?
Okay.
And one of those that's really easy to sort of think about and picture is biomass, and thinking about trees and other plant matter, and how can I use this into products. And if we go back to, I think it was about the 2015, 2016 timeframe, you had Maine actually go through where about 5 of the different paper plant production facilities closed down, and it was a big emergency for the state of Maine just because of how much they do with wood products. And Soydan Askan, who is one of our researchers working this space, he had been studying, if you break down plant matter to its fundamental basics, it gets into these things called nanocrystals and nanofibrils. I think for the listeners, the most important aspect of that is they have some really nice structural properties to them.
At the nanoscale, right?
At the nanoscale, and you could put those into polymers and actually get engineered products out of it. And so what we did was saying, could we start to augment and create value-added products with them? And they also do a lot of work in paper and processing of wood products to break those down. They were just getting started into heavy and large-scale polymer printing, and actually brought those two together and started looking at high deposition rates of bio-based materials to build up structures. And areas we're thinking about are things like packaging, thinking about buildings and structure. And when I say that, you think about a home, and we have a huge deficit in our homes at this point. Can we start to go through and actually augment or implement some automation in even the construction area as well? And even think about industrialized construction. We actually 3D printed a house. It's about 600 square feet that is all based off of bio-based materials. It is essentially got wood flour in it into a bio-based polymer, built the whole house in 3 sections. We're able to go through and basically assemble that in about half a day because we'd already printed the parts, and then finished it all out for the next couple of weeks after that.
Unbelievable. So if you think about boiling that down a little bit into the subcomponents of what you just talked about, I mean, first of all, when we think about sustainability and locally sourced products, right? So if you're able to build these polymers out of locally acquired nanoscale renewable products, right? So these are all things that if I'm talking about a plant that's renewable right at the location, and we think about, whether it's extractive mining, or we think about all the transportation that goes into moving materials, all of that drops out of the model because I've got the materials that are being created right near the source of consumption or the source of use. And then I'm taking those materials and I'm using additive manufacturing in this case to basically 3D print. You said a 600 square foot house, which is, incredible. And just, it's like a tiny house that you're 3D printing out of locally sourced materials. And it's completely sustainable, completely renewable, and really kind of speaks to the future of, what the technology can look like in terms of other applications of that technology. So 3D printing a house would be one of them. Are there other things you're thinking about, Bill?
Yeah. One of the biggest areas we found at the MDF, as well as the Maine, we get a lot of industry that comes in. In fact, I get about 1,100 companies that visit the manufacturing demonstration facility, or MDF, per year, every year.
1,100.
Yeah,
Incredible.
1,100.
Yeah.
So we get a lot of information from them.
Yeah.
And tooling, molds, dies, jigs, fixtures is a big area that we've less about cost. It usually has to do with lead time and the speed of innovation, the speed of fabrication. And one of the things we've looked at is being able to create recyclable, low-cost molds. So one of the areas we've worked with is the boating industry, Maine, where you can go through, fabricate the mold now, and then use that mold to build your boats. We've also done that with the precast concrete industry and gate construction, where we actually, if you're ever in New York, see the Domino Sugar Building.
Okay.
The entire concrete facade was built using 3D printed molds.
Wow.
There's about 65,000 pounds of material. That's led us to recycling as well as sustainable material practices like bio-based materials to go through and look at those molds and whether we can bring down the cost of this upfront material by using those bio-based materials.
I love that. I mean, you think about the world of manufacturing that I spent all my time in, and you're trying to innovate at speed, and then all of a sudden you build a new machine tool, or you need a new machine tool, or a mold, or a fixture, or work holding device, what have you. And, you go to some company, maybe in the US, maybe in Asia, who knows, and the lead time is 3, 6, 9 months to get that. So now all that innovation stands still. And what you're saying is that we can do that with locally sourced components in real time in a way that we don't have to necessarily wait for somebody to build up that fixture. Could certainly see how that works in the marine industry, in the construction industry, and so on. So great things coming from this partnership with the University of Maine. I know that's not the only partnership you have, and in as much as you and I are recording this episode at the International Manufacturing Technology Show here in Chicago, Illinois this week. You referenced that a little bit earlier. The last time we were here, which this show is every 2 years, we interviewed every single USA National Manufacturing Institute. And I know you're involved with one of them, that's IACMI, and that's all focused on workforce training. Give our audience, if you will, a primer on the manufacturing institutes, and then tell us about this partnership.
Oak Ridge heavily supports quite a few of those. I personally spent a lot of time with Manny, which is cybersecurity.
Yep.
SESME, that's the smart manufacturing.
I know him well. In fact, John Dyke's been a guest on the podcast, the CEO, great guy. Yeah.
That's great. In fact, we're going to have our annual, SESME's annual meeting will be at Oak Ridge this year.
Oh, well, really?
Yeah. So
you'll keep your eyes open for their new smart manufacturing trainer. I don't know if you've seen that or not. SESME has a smart sensors trainer around smart manufacturing, and when they're there, you should check that out.
That's great.
Really cool.
We'll go through that. Yeah. IACME is one that we helped found at the very beginning. It's in composites. And as we've worked with IACME, we've looked at how do we lower the overall cost for carbon fiber, for composites, and show how we can start using it for application for energy use.
What is an application in energy for carbon fiber or for composites?
So most people, when you think about carbon fiber and composites, you think about aircraft.
Right, or race cars, or
race
bikes
cars.
In my case, bicycles. Yep, absolutely.
Actually, the largest national need for it is in wind turbine blades.
Interesting. Okay.
And it's actually for the wind turbine spars explicitly, but it's a huge application, and it's growing as we continue to build more and more wind energy turbines.
Right.
And so what we've tried to do is understand the precursor, which is about half the cost, how we can lower the carbon fiber, and then come up with automated approaches to fabrication of composite components. So everything from fiber to composites, we've been doing work in that space, even using smart manufacturing on the carbon fiber production, which is not something that you typically see with a lot of carbon fiber production.
What's an example there?
Visually being able to look at the fiber as you're producing it, and being able to actually tell certain features when it comes to oxidation, graphitization, to make sure that the fiber is going to have the mechanical performance you're expecting out of it. It's visually looked at as we're going through and able to make real-time changes through those process parameters as you're going through and looking at.
So you're not only like doing predictive analytics, but actually changing the manufacturing process based on the data that's coming through. That's really cool.
Yeah. And so with IACME, we've spent quite some time with them working in that space. And one of the things we've done is work with them for some of the different workforce development activities. If I take a step back regionally, we're very close to the University of Tennessee. And even though we have 50 different partnerships with universities, we've been able to form up and create what we call their governor's chairs. This is something that the state of Tennessee has brought in, where the professors are half-time at UT, half-time at Oak Ridge National Laboratory. Yeah. One of those is Uday Vidya, who is the Chief Technology Officer for IACME. As we've gone through, we've gotten to connect with IACME in looking at that workforce element. And that first started in what we were doing on the composite side, but that has grown. And one of the biggest areas is machining. Back in, I think it was about 2018, 2019, there was an executive order to look at machine tools and the concern over where machine tools was going. We led that and brought some great talent from across the nation to come together and talk about it. That spurred on the America's Cutting Edge, which is a Department of Defense IBAS, which is industrial base and assessment sustainability, and went through and worked with them to basically put together this America's Cutting Edge program that's at Oak Ridge and at IACME to train people. And it's made up of a couple different elements. One is we went through and put internet curricula. And one of the other parts of this that was really important was the fact that we didn't want it just to be for collegiate level, or we really wanted to get more people engaged with this. So this is being an online, it's free. Yeah. Anybody can go over and do it. It's about a 6-hour course.
What are the learning outcomes? What are people learning?
So they're learning about advanced methods and knowledge base in the machining process itself. Certain things like how the cutting head, the angle can change the shape of the chip, the efficiency of what we're doing.
Sure.
We've also tied into it some of the various activities at Oak Ridge within that. In fact, one thing that started off as a tech collaboration from the MDF that has led into part of the ACE program was actually working with MSC. We brought in about 13, 14 MSC regional tech managers that came in. We took a concept of if you do a tap test and look at the acoustics and look at an accelerometer, you can actually look at the efficiency of the cutting of the system.
Wow.
And went through, created an app for this, and it can improve cutting rates by 2 to 5x.
Wow. And that's an app that would be used by a contract machining company or who's
So MSC, and this is an important one because sometimes getting into small companies, it's hard to implement or engage on certain smart manufacturing practices, or you're worried about buying equipment or what have you.
right?
In this case, MSC actually offers this as a service to those that are buying the tools from them. So they will come in and actually perform this with you and then show the optimization.
Okay.
And in the first couple of years, they had, I think, a little over a $20 million savings for those companies
Wow.
just based off of doing this, and are projecting that it'll be about $750 million worth of savings long term
Unbelievable.
through using that. So that's something that's come out of that activity as well.
Right.
We've had about 10,000 people participate on the online curriculum, and it's actually broadened to do metrology as well as machining, composites, and a couple other areas as well. There's also, though, a on-site. So after you go through and do this 6-hour course, if you have interest, you can actually set up for an on-site. And there's 36 different locations through the nation that they've done, and had about 1,800 people perform the 1-week on-site education activity as well, hands-on.
So you're taking some really complex concepts, right? We're talking, I mean, think about all the things we've talked about: nanoscale technology, carbon fiber, accelerometers, acoustic testing, all these other complex concepts, and boiling it down into, it sounds like some bite-sized pieces that could be understood by anybody with some modicum of manufacturing understanding or materials understanding. Tell us about the magic of how you do that. How do you take this really complex stuff that you're working on and kind of distill it into something that makes sense to somebody that's accessing it via e-learning or the 1,800 people that attended this event that you had?
Yeah, so one of our other governor's chairs, his name is Suresh Babu, actually laid out several years with us a braided rivers approach is the way he called it. The concept is that as you go through and look at education, I want multiple different approaches that are hitting different individuals as we think about this, that there isn't a one-size-fits all.
Right.
And so that's led to everything from us having internship programs. We typically each year, Oak Ridge is a total has about 1,000 people. We have about 100 people, 50 to 100 people over in our space specifically that are working on these advanced manufacturing technologies.
Wow.
The benefit of that is hands-on activities, getting to try out the equipment, really getting to learn from it, not just classroom learning, but actually getting hands-on on that. We also had an internship program for technicians that would work on the equipment with the idea that when they finished working with this, they would then go on and take jobs outside. And so looking to see how we spur that on, connecting with the various different schools we've talked about. And then UT, we've had anywhere from 60 to 150 students that are engaged, that are local, working within the ecosystem, whether that's IACME, Oak Ridge, what have you.
Awesome.
Each of these have had different aspects of how you go through. A lot of what we're doing is heavily in the sciences, and that's not what you're necessarily looking at from the industry standpoint. I talked about the number of companies that come in and work with us. That's important for us to understand what's important to them and how we translate those activities. And that also goes back to the equipment manufacturers working on the floor with us, so we can see
Right.
how do these actually work into the machine itself, and what are the things we need to be educating or working around as you start doing that.
And you're focused on what is important to the individual manufacturers. You suggest 1,100 of them a year that are coming and engaging with the work that you're doing. What are you hearing from them about their biggest workforce challenges?
The workforce challenges that we've seen as we've gone through, a lot of the interest has been on that hands-on. In fact, one of the things that we did with Maine Maine actually started a while back a merit badge type of process to go through, and it was not just to show the classroom, but actually get hands-on training. They've opened that up to getting these badges for actually time on the large-scale printing machines and some of the other composite equipment, and being able to have sound amount of time between 100 to 300 hours of application on those machines to start showing a certain proficiency associated with that.
Sure.
And I think that information has all been fed from industry to Maine to lay out what is it that they want those students to actually learn from it.
Are there specific areas where they're saying, hey, these are the things that these are the kind of the skills or the competencies we really want our workforce coming to us with?
For them, work in the biomass and understanding some of the wood products, understanding the 3D printing and how to operate additive machines were actually things they were asking for. Within the composites, part of the reason we've gone heavily into the machining area is that skill set in machining and making sure that we continue to have a large demographic that understands machining. That actually was part of the executive order findings when we went through and did it, was just the average age of what we're seeing in the machining area.
Right.
And
Scary.
trying to bring more people into that space with a core knowledge of how, machining practices, modern machining practices, and what they could be learning from that area.
Well, and I think that's a key part of it. When you think about young people considering careers in manufacturing, it's interesting. If you look at all the data, the number of young people that want careers, quote, in tech, right? And it's like, depending on the survey, 60 to 80% of students are saying, I want a career with a tech company. And then you think about the kinds of technologies that you're talking about here and the kinds of intricate sciences that you're working with, the research you're doing, the future of manufacturing, all these different applications. The number one space for tech careers, in my opinion, is in manufacturing. If you want to work in tech, there's a place for you in manufacturing, as all these technologies are advancing in the ways that you're describing. So a message to all of our students that listen every week and to their teachers, make no mistake, manufacturing careers are absolutely tech careers. And you've got all kinds of manufacturers coming to you with these really complex challenges that they're trying to address with that next generation of talent. Give me an example, if you would, of a really off-the-wall kind of unique question or challenge that a manufacturer came to you with.
Lockheed Martin, when they came in, they had just gotten into large-scale polymer printing. They had already started to adapt a way for extruding it and trying to make large parts with it. We got engaged with them to understand how could we start increasing the rates of production. It was very small at that point. We started looking at screw extruders and gantry systems to keep up with the pace and start getting into really large systems from this. As we started to develop that, we found you had to redefine the extruders, you had to redefine the materials as we went through. Local Motors saw we were doing this on a homegrown system and signed up for IMTS actually to 3D print the car, the Stratty that is outside.
Yeah, cool.
We had a 6-month or 8-month window to try to do that. Very quickly had to connect, at that point, was with Cincinnati Incorporated, where we utilized their gantry-based system. It had the right head ability to carry the weight of the extruder and could move at the right rates as we did that.
So 6 months to figure out how to 3D print a car.
Yeah, 6 months to go from, I don't have a printer that can do this, to going through and actually being able to print. In fact, we didn't get it quite right until we were actually here at the show.
Oh, wow.
The screw extruder that was developed, that was at that point about 40 to 60 pounds per hour. Like I said, we're up to about 500 pounds, just to give you some order of where that is.
Exponential economy, and that's how it works.
And before that, we were at like 10 to 12 pounds per hour. You weren't able to go through, and actually the first couple times we printed the car, it would, even in quarters, it would crack up on us. And so we really had to develop or very quickly change the entire printer itself and develop the materials. And part of the reason I say materials is you actually had to put about 20% glass or carbon fiber to keep the coefficient of thermal expansion low in the polymer to actually keep it from not pulling up on you and cracking or distorting the shape. So that was all done very, very quickly. And it was this
Awesome.
scenario between Lockheed and then later having Local Motors say, I'm challenging you and we need to go through and see, can we do this?
Yeah, well, when you think about the companies that you've mentioned, companies like Lockheed Martin, we talked earlier about GKN, talked about Lincoln Electric. I mean, you're working with some really, really cool companies. And it speaks to, again, this incredible opportunity we have to upskill a generation of manufacturing talent. Let's turn the clock back or ahead, I should say, and dream a little bit, Bill. 10 years from now, even as we look at the skills that are going to be important in manufacturing and those types of careers. When you sit down with, I'm sure you've got tremendous numbers of students that take interest in the work you're doing as well. What do you tell them about the future of advanced manufacturing and what they should be thinking about?
I think to be open-minded and connect in a multidisciplinary team.
Mm-hmm.
Industry typically does this and pulls together what different backgrounds they need as they're going through and looking at it. However, in our education system, as well as at the National Laboratories, we don't always, it's sort of birds of a feather flock together,
Right.
and doesn't integrate. And frankly, the strength of what we're seeing comes from that multidisciplinary team. We've even had internally concept of looking at, I'll call it the Renaissance person, how many different areas of development and different projects can you get into? So keeping that open mind of learning new things, integrating the skill sets from, I think is important as you look at this rapidly changing manufacturing area, and pulling those different strengths together and knowledge bases together, I think is really important for our future workforce.
Well, and it really speaks to how the world of work in manufacturing is changing. Your use of the term multidisciplinary and really thinking about, somebody working in manufacturing 30, 40 years ago, maybe even 10, 20 years ago, there was a place where you could step into running a machining center, working on an assembly line, working on a powder coat booth or so on. And if you wanted to, probably have that job for almost your entire career. And now we think about how all these technologies are changing, how we have to pull people together from different parts of manufacturing, making sure that people have the understanding of, I may be an expert in additive, but I need to understand subtractive, or I may be an expert in subtractive or machining, but I probably need to have a knowledge of metal stamping or fabricating or joining or what have you. So all that interdisciplinary work, being able to work as a team, really, really important. And I think you're right, as we think about the importance for multidisciplinary interaction, the importance for understanding speed in manufacturing, not just in terms of the production process, but in terms of innovation, in terms of bringing products to market and so on. So it is going to be an exciting time to be in manufacturing. Again, whether you're doing the incredible research and leadership that you're involved in, whether you're involved on the manufacturing shop floor in terms of producing parts, this is a really exciting time to be a young person. And that's kind of where I want to finish our conversation, Bill, is kind of turning back the clock to the time when you were a young person, maybe considering your career. And as you and I were talking, and as we've discussed, had an opportunity to live all over the country, experience a lot of different cultures, a lot of different people as you were growing up. But I want you to go back to 15 years old, your sophomore year of high school. If you could go back to that young gentleman all those years ago and give him one piece of advice, what would that piece of advice be?
What I would say is, really, as you start to go through, be open to those things that make you uncomfortable. The biggest thing I've seen is growth opportunities in my own individual life are those when I was on the edge or not comfortable moving into new areas that really stretched your thinking or challenged you. And I think as we look at this acceleration of adoption and technologies changing, I think one of the most important things is leaning in and stepping into it continuously. I think that's the biggest piece, is resistance or not jumping into it with both feet and trying to take a hold of it and then doing it again and again as you have new opportunities to do so.
Especially in this day and age in which we live, where we've got so many technologies coming at us, and not just the smart manufacturing, not just materials. We talked about artificial intelligence, machine learning, automation. And I think there is a situation where a lot of folks look at all that and they become a little bit uncomfortable. And rather than running from that, we need to embrace the uncomfortable and embrace what the future holds for us, because it is a really, really exciting future. And I can't thank you enough, Bill, for spending some time with us talking about that future. Our guest today on this episode of the Tech Ed Podcast has been Dr. Bill Peter. He is the Director for Advanced Manufacturing at the Oak Ridge National Laboratory. I want to thank our audience for joining us. If you love this particular episode as much as I did, talking so much about research and advancing manufacturing technologies in general, please visit us wherever you get your podcasts and leave a review. Give us 5 stars if you're so inclined, whether that's Spotify, Apple Music, or any of the 45 platforms on which we stream every single week at the Tech Ed Podcast. We would love to hear from you. And we'd also love for you to check out the show notes from this episode of the podcast. We have the best show notes in the business, and you'll find this particular episode's show notes at techedpodcast/Peter. That is techedpodcast/PETER. My name is Matt Kirchner. I am the host of the Tech Ed Podcast. Thank you so much for being with us, and we will see you next week.